Let's look at a particular application of one-dimensional motion, which we call freefall. This is for cases where, remember, we had 5 equations of motion, and they're all assume that the acceleration was a constant. What we're going to be doing is we're going to pick a very specific value for the acceleration. And we're going to redefine this acceleration for the case where it has that specific value. We're going to redefine it as g. So g is an acceleration which happens to have a very, very specific value, which will be 9.81 meters per second squared. That's what freefall is. Now, the only thing that we need to know about the cause of this acceleration, that is what creates it, is that, and we will see this in other chapters when we see forces. All we need to know is that this acceleration is being created by a particular force which always acts from the top to the bottom. Therefore, the direction of that acceleration is always from top to bottom. So if we decide to have a standard coordinate system x, y, and since we're doing one-dimensional motion, just the y axis. If we decide y to be going up, a, since it's going down, will have a negative sign, and therefore the acceleration is minus 9.8 in the j direction. I would suggest to use this particular type of coordinate system. Of course, you don't have to. If you decide to choose this as your coordinate system, then it will be for you plus 9.81 meters per second squared. So depending on the coordinate system that you pick, you will either keep the minus sign or not. Again, I would suggest that you stick with the conventional coordinate system, which is positive going up. So I'll do everything based on this type of coordinate system. So let's review our equation of motion. I'm going to rewrite them on the left side. We had, we had V is equal to V naught plus AT. Then we had X is equal to X naught plus VT. Then we had X is equal to X naught plus V naught T plus 1 half AT squared. And then we had V squared is equal to V naught squared plus 2ax minus x naught. And I'm going to stick to those 4. So since we're dealing in one dimension, and I'm going to pick a dimension which is up and down, because since A is directed down, it would be boring to select left and right, because you would have no say, and I would be stuck with just this equation. So freefall case is the case where the acceleration is 9.81, so I know its specific value, and if I choose this as my coordinate system, the magnitude of my vector acceleration is minus 9.8 in the j direction. So what we do is we're just going to take all the equations that we had and just rewrite them to fit our case. Whenever I have a v, I know that I'm moving either up and down, therefore this will be my vy. Whenever I have v naught, this is my initial velocity, again in the y direction, because this is the current system that I'm considering. Whenever I see a, since I'm using a coordinate system being positive going up and my acceleration is going down, therefore opposite to my coordinate system, whenever I see a, I will replace it by minus g and then t. So again, this version is only consistent with a coordinate system going positive up. I'm going to do the same thing for all the other equations. The second equation will give me y is equal to y naught plus vyt. But this doesn't apply to me because, again, remember that this equation is only true if a is equal to 0. Since I'm looking at the case free falling where a is not 0, but a non-zero value, this formula just disappears. So I don't have any analogy for that one. But I can do the same thing for the other guys. And I'm going to have, whenever I see x, I'm going to put a y because I'm using the y direction. X naught will give me y naught. V naught will give me V naught in the y direction times t. I'm having a, so I'm going to replace it by minus g, 1 half gt squared. And for the last one, v squared is really the y component of v squared. V naught squared is v naught y. I see a, so I'm going to replace it by minus 2g. And x minus x naught will give me y minus y naught. Those are the equations that you can use for one-dimensional motion for the case of freefall.